Greetings, we are continuing with our lectures in thermodynamics, and today we want to look at some basic equations in one-dimensional flow. So let's look at the basic equations. Basic equations. And as you have already seen in our many lectures, the foundational equations are the first law of thermodynamics and the second law of thermodynamics and the principle of conservation of mass or continuity. So we must get these particular expressions in their differential forms. So we want to write the first law of thermodynamics in its differential form and the second laws and of course the principle of conservation of mass, this continuity equation in the differential form. So the first thing is we need to express first law, second law of thermodynamics, and the principle of conservation of mass. Of the continuity equation in differential form. Now you recall from our earlier lectures, and I encourage you that you go through our lectures systematically so that we are together. For the first law, remember, for the first law, we say that dH plus dC squared over 2 is equals to dQ minus dW. And remember, C represented velocity, and of course H has the usual meaning, which is enthalpy, and Q and W are heat and work. And don't forget always that heat and work are actually path functions. H, for example, S, as we have always said, the path is a state function. So, in the case when you are dealing with, for example, a diabatic flow in a nozzle or a diffuser, in the case of a diabatic flow, in a nozzle or diffuser, and you can check our earlier lectures where we described, we had worked on nozzles partly. So in the case of a nozzle or a diffuser in an adiabatic flow, then that particular expression will be dH plus dC squared over 2 is equals to 0. Don't forget that we have the potential energy expression, which has to do with elevation. So we are assuming that elevation is not a factor. This is potential energy, and that's to do with elevation. So we are assuming that elevation is not a key factor. That's why we have ignored it, and we have gone ahead and worked with dH plus dC squared over 2, and that is equals that. So in the case of a diabatic flow in a nozzle or diffuser, then those terms on the right will vanish, and so we have dH plus dC squared over 2 is equals to 0. So if we proceed again, we can proceed further and use other thermodynamic properties to break down this particular expression, and the one which we'll build up from is the definition of enthalpy. We know that enthalpy H is equals to U plus PV. So if we take the differential form of enthalpy here, then we'll have dH is equals to du plus P dV plus V dP. So we have just used the product rule. Remember, don't forget the product rule. We say duV will be U dV plus V du. Always remember that. That's very, very important for us to remember. So that's what we have used to expand that particular quantity there. And remember from first law of thermodynamics, Remember from first law of thermodynamics, du was equals to dq minus dw. And what is dw? dw is, in the case of PV work, is minus pdv, and dq is the heat. And if we are considering the second law, where we talk of entropy, then based on Clausius inequality, we know that dw is equals to minus pdv, and based on Clausius inequality, which we have also talked about repeatedly, we know that ds greater or equal to dq over t, or what you can say is dq is equal to t ds, where s, remember, is entropy. S is entropy. Very important. So if you plug in those expressions there, which you have just gotten, so here we are working with the second law of thermodynamics. So what are we saying? Then we are saying that dH therefore will be equal to dq is tds, dw is minus pdv plus pdv plus v dp. Of course, these two terms cancel, so you have dH is equals to tds plus vdp. So if the process is isentropic, in other words, there's no change in entropy, then this term will vanish. If process is isentropic, that means ds is equals to 0, then dH will be equal to v dp. So those are fundamental equations which I've gotten there. And so if we link this particular equation with that particular equation there, in other words, in place of dH, we can put v dp, then we will have v dp plus dc squared over 2 is equals to 0. If we rearrange that particular equation, which is a very simple equation, then we see that dc squared over 2 is equals to minus v dp. Now, if we have a plane, remember, and I encourage you to go back to our earlier lecture on one-dimensional flow, and we defined what one-dimensional was. If we assume that there's a flow between two planes which are separated by an infinitesimal distance, you have two planes separated by an infinitesimal distance. Then, in that particular case, the flow between them will be the integral from plane 1 to 2, the lower limit, upper limit, 1, 2, where 1 and 2 represents plane, so this plane 1, that is 2, over 2, will be equals to minus the integral of v 1 to 2 v dp. So this simplified will be c2 squared over 2 minus c1 squared over 2, that will be minus integral from 1 to v dp. That will be minus, that's the integral, the c2 squared over 2, that will be minus c1 squared over 2. Now, so far so good. Let us look at how we get the differential form. How will we get the differential form? And of course, this right-hand side expression is always easy to get because you have always gotten, remember, we always have for fluids. For fluids, we always have an equation of state relating pressure and volume, so it's solvable. Can be solved knowing the equation of state. And there are always equations of state relating pressure and volume for fluids. Now, when we come to the principle of conservation of mass in its differential form, recall where we're dealing with the principle of conservation of mass, we had said that A1 C1 over V1 is equals to A2 C2 over V2, so we can say that's a constant. And of course, that's cross-sectional area, that's velocity, that's specific volume, don't forget that. So if we take the logarithmic form, using the identity, don't forget, when we said log of A, B is log of A plus B, log of B, and log of A over B, log of A over B, we say is log A minus log B. Remember this identity, very important. So we just apply it there. So we'll have, applying that particular identity, then we'll have log of A plus log of C minus log of V is equals to a constant. So if we differentiate this logarithmic form, if we do on differentiation, we will get dA over A plus dC over C minus dV over V is equals to 0. Recall and remember, always remember, and we have worked with that this quite extensively throughout our lectures. Always remember that the integral of dx over x was natural log of x plus c. Of course, that's the integration constant because we are not put any limits there. Always remember that. And so when we differentiate these logs, we get dA over A, dC over C, minus dV over V. So we can relate, for example, the cross-sectional area to the velocity and pressure. The velocity and pressure. So therefore, relating cross-sectional area and velocity to pressure, we will have dA, just rearrange the quantities, is equals to dV over V minus dC over C. But remember, we have already, unfortunately, we have rubbed out that expression. Remember, we have the expression dH plus dC squared over 2 was equals to 0. And we have said that was V dP. That we said was V dP. So, dC squared over 2 is equals to minus V dP. And so, working with this particular expression, if we cross multiply, we have dC squared is equals to minus 2V dP. If we divide by C both sides, then we'll have dC is equals to minus 2V dP over C. And so we can plug in this dC into our expression there. Let me see if the clearer pen. We can plug in this dC into our expression here. We're going to plug it there. We're going to plug this expression there. So we have, therefore we have dA over A will be equal to dV over V minus, and remember there's a minus sign there, so it becomes plus 2v dp over c squared. We've just plugged in the expression. We've just plugged in the expression for dc into that particular expression there. That particular expression there. Now, when we have a pressure wave in a fluid, the velocity of that pressure wave in a fluid, and that's a fundamental concept in fluid dynamics, which we will not delve in here. When you have a pressure wave, so when we have a pressure wave, in a fluid, the velocity can be expressed as a squared is equal to a squared c squared will be given by a squared, and we'll have that as c squared del p del v and a constant enthalpy. So that's just a definition we have there. So if we look at our system here, we can rearrange this, make it dA over A is equals to, if we put VDP outside, so we'll be having dV over VDP times V. So we've just factored out VDP, and so if we have factored it out, then we have, of course, to divide this by VDP, so that if you multiply this with this, you still have your dV over V, plus we have 2 over C squared. 2 over C squared. So that this expression is VDP into, this is now dV over dP V squared plus 2 over C squared plus 2 over C squared. This dA over A. And so that particular expression there, this is V. That particular expression there, we can now put in the velocity of the pressure wave. We can put in the expression for the velocity of pressure wave, which is given by where we have V squared, the change in pressure with a specific volume and a constant entropy. Remember, these are partial derivatives. So when you have a partial derivative, the subscript written outside the bracket is kept constant. So there's change in pressure with volume and a constant entropy. So if we substitute this expression here, if we substitute that expression there, then we have dA over A will therefore be equal to VDP into, so we'll have 1 over A squared plus 2 over C squared. Now, what does this mean? What's the import of this expression here? So if we have case of acceleration, if you have case of acceleration, as will be the case in a nozzle, remember, in the nozzle we have high pressure, comes out as low pressure, low velocity, comes out as high velocity. So in the case of acceleration, which is in the case of a nozzle, then dP will be negative. And in the case of deceleration, as in a diffuser, because the reverse is true, dP will be positive. And the case where the velocity is constant, constant velocity, dP will be equal to 0, in the case of constant velocity. So you notice here we have related the cross-sectional area to velocity and pressure. And we have given its interpretation in terms of when you have acceleration, that's increase in velocity, deceleration, decrease in velocity, and in the case of constant velocity. So those are just simple basic equations in one-dimensional flow systems. So let's stop at that point. We are continuing with our lectures.